Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Decision-Making Artificial Intelligence, Optimization of the Poultry Supply Chain. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. Enterprise-wide optimization. Enterprise-wide optimization. A company's value chain is made up of two chains, strongly interrelated. Demand chain determines all the processes that are carried out to attract customers in the markets, and supply chain determines all the processes that are carried out to produce the products that customers want to consume. The diagram presents the chain of the company's production chains that together make up the value chain. One of the greatest evolutions in the modeling of companies occurs in the interpretation of their value chain. The diagram presents the evolution of different administrative practices in companies, which are linked to technological solutions, leading to AWO. Thanks to computational power, the integration process has continued to grow. The diagram presents the original S&OP model, and the current version, which integrates more and more models. The integration of all models is done through a database with a common data model. Given the principles of the artificial hypothalamus, in Industry 4.0 all models can be run in parallel in real time. Artificial hypothalamus of a company integrated in the poultry sector. Artificial hypothalamus of a supply chain, based on facilities. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. Modeling the poultry supply chain. The entities that are part of the poultry supply chain are farms, places where birds grow. Sheds, covered facilities where a group of birds of the same breed are reared and fed together. Nutrients, basic foods that birds need to be able to develop. Concentrated feed, commercial products that provide the nutrients that birds need. Concentrated feed plants, produce concentrated feed. Sacrificial plants, place where birds will be killed. Cutting plants, plants for handling birds that have been euthanized, whether they break into pieces or not. Meat plants, plants where whole birds, or in parts, are processed to produce commercial products. Commercial products, poultry must be converted into commercial products, with defined quality characteristics, to meet the demand for parts and whole birds, and orders, product demand, quantities, and delivery dates. From a flow point of view, the supply chain is made up of two links. Primary, located on farms where birds grow, and industrial, made up of the industrial plants that are used to obtain commercial products. These are slaughter plant, cutting plants, and meat products plant. Finally, poultry products are delivered to a market, through distribution channels. Network of farms in a poultry supply chain. It all starts from a prototype model to represent farms. All the mathematical models are built, for each of the farms that make up the primary link, and they are connected to the mathematical models of industrial plants, which are used to process the birds, until they are converted into commercial products. Poultry farm production optimization. Challenge: plan the optimal allocation of sheds in a poultry farm. Solution: a mathematical optimization model that considers the integral process of animal growth, food supply, cost of production, and selling price in a market with dynamic demand and prices. The poultry product supply chain includes the following facilities: rearing farm, laying farm, incubation farm, fattening farm, and storage and sale of live chickens. As a complementary facility, it is common to find the feed plant. On farms and in industrial plants, the following activities, or stages, are carried out. From the incubation process, production is divided into two. For breeding and breeding, the aim of which is to maintain the population of laying birds. The eggs are divided into fertile eggs that return to the incubation process, and commercial eggs, which are destined for the industrial plant and later for the market. For fattening, the goal is to provide live animals that become commercial products. The poultry will pass through the following plants: sacrifice fattening, and transformation. Industrial bird reproduction is a controlled genetic process, spanning 3 generations. Grandparents breeders broilers. When broilers are not purchased, the production is directly related to the number of grandparents and active breeders. Therefore, this genetic process is part of the company's planning. During poultry farming, the molting cycle refers to the natural process in which adult birds lose and regenerate feathers, which typically halts egg production for 8 to 12 weeks. Egg supply chain. The production chain begins at the breeding farms, where fertile eggs are obtained, which will give rise to commercial birds, and commercial eggs, which will be sold directly on the market. Tactical farm network planning. Models aimed at optimizing the development of production processes in the network of farms, hatcheries and fattening. They must coordinate the growth process of living things, located in sheds, with commercial products that are expected to become at the end of the supply chain. Biofarm is the model developed by Hive for tactical planning of the primary link, simulate and optimize the genetic process to balance the production chain of the different types of animals, which are required to support the production chain, and the growth process of birds considering consumption of balanced feeds, conversion of food into nutrients, use of sheds, commercial products, and capacity and location of industrial plants. Biofarm optimizes the main link in the chain in maximum detail, to carry out effective farm management, considering the effect of climate and soil, the forage production cycle, the life cycle of the animals, nutrition, mortality rate, feed consumption and/or the type of grazing. To do this, a typical mathematical model is developed, which represents the production conditions on farms. From the model, it will be possible to determine the optimal life cycle for different types of conditions in the farm environment, where the productive process takes place. The idea is to synchronize production cycles on farms with production activities in industrial plants. To do this, a prototype mathematical model is developed, which parametrically represents the production conditions on each individual farm. From the model, it will be possible to determine the optimal life cycle for different types of conditions in the agro-industrial environment where the production process takes place. Based on the generic model for farms, the implementation process is designed for the network of farms, each differentiated by its microclimate and microenvironment. This implementation covers company-owned farms as well as those of third parties with which it has trade and technology transfer agreements. The company must be able to exercise control over the decisions of third parties, expanding its field of action in a cooperative manner. The idea is to synchronize production cycles on all farms with production activities in industrial plants. This will prevent an imbalance between the demand for commercial products and the supply of living beings. Failing to optimize the integrated network and instead optimizing each farm individually is a big mistake, as it will lead to a surplus or shortfall in demand, preventing the profitability of the company's supply chain from being optimized. In other words, there is a lot of money left on the table. The structure of the poultry production networks can be organized hierarchically. Regions, areas, farms, and sheds. The atom of the network is the shed, which is where industrial activities are carried out, and at that level the planning of the farms must be defined. In this way, the model will provide, for each shed, on each farm, condition of the house, in production or disinfection, or inactive, breed of the bird, number of birds, age, and date of slaughter. The shed cycles include the cleaning and disinfection of poultry sheds after a flock is removed to prepare for the next one. At the feeders, this cleaning cycle is carried out approximately every 7 weeks, while laying hens molt naturally, often in autumn, periods that are repeated indefinitely, varying the disinfection time. For a good characterization of the weight function, predictive analytics methodologies should be used. The most used methods are artificial neural networks, machine learning, and advanced probabilistic methods. If parental habits change, such as a change in diet, this dynamically affects the characterization of function. The volatility of bird weight throughout their age should be carefully planned, as the attention of the markets depends on it. This estimation process must be carried out using predictive analytical models that provide the probabilistic distribution of the bird's weight as a function of age. The production cycle of the birds is decisive in all the planning of the company, since as a raw material it presents peculiarities that cannot be ignored. One of them is the uncertainty in the conversion of inputs into outputs, as is the case with nutrients and the weight of the live animal. To analyze the case, the life cycle of a possible broiler chicken is taken as a reference. In this case, the hen has 3 weeks of incubation and develops in the shed for 7 weeks. It is born with 50 grams, and in the 10th week of the process, with an age of 7 weeks, it will weigh, on average, 1,200 grams. To have a realistic view of the problem, the uncertainty in the conversion of nutrients to live weight must be characterized in a probabilistic way. In this case, the 2 dotted lines indicate the range of variation for the weight of the live birds. The probability distribution of live weight must be associated with the technical specifications, qualities, of commercial products. In this case, 3 qualities, A, B and C, are a function of the weight of the chicken. The volatility of weight means that birds of a given age can meet the demand for multiple products, with different qualities, or that the demand for a product with a specific quality can be met with birds of different ages. The shaded area determines the viability zone of the solutions, which can exist to meet the demand for multiple products, with multiple qualities, by birds of different ages. Commercial products and weight ranges. Perhaps this corresponds to the biggest problem that SYGEA must face, since the characteristics of the market depend on many factors that make it very varied. These factors may depend on regional, geographical areas where the product is consumed. Economic classes that consume. Seasonal, the time of year in which is consumed. Combining solutions for a large company becomes a fundamental issue in decision-making planning that affects the entire production chain throughout the year. To visualize the complexity of the problem, the relationship of the chicken weight function with the quality specifications of SYGEA's commercial products is presented. The problem is complicated, and grows as the company grows, since factors such as nonlinear weight functions, microclimate on farms, multiple breeds of birds, and the dynamics of demand. The table presents an example of the annual and weekly planning of the 10 sheds on a farm. In blue, the week in which a litter is started in each shed and the number of birds is indicated. Optimization provisioning of concentrated feeds. BioBFR is a set of models aimed at optimizing the planning and scheduling of the supply of balanced feed, or fertilizers in the case of plantations, to the agricultural network. The age distribution of living beings on farms determines the type of nutrients they require. Therefore, they must be coupled to agricultural network optimization models. If the concentrated feed plant is part of the company, the planning will be carried out by the company. If it is not, it must sign bilateral contracts or buy the concentrated feed available on the market. The process includes food formulation, considering the availability of raw materials, and the planning of the distribution of food to farms, taking as a reference the transport costs and the capacity of the vehicles to be used in the process. At the tactical level, the models determine balanced feed consumption goals. At the operational level, the models establish in detail the transport services that are required. Concentrated feed formulation starts with nutrient-rich raw materials, such as soybeans and corn, which provide basic nutrients such as energy, protein, and methionine. Normally, the exact basic nutrient content of a raw material depends on the batch of the product purchased. On the other hand, animals require specific amounts of nutrients, which vary depending on age. In the example, the following are considered: crude protein, crude fiber, crude fat, calcium, and phosphorus. Concentrated feeds must contain the specific nutrients required by animals, based on the mixture of multiple sources of raw material, and possibly additives. Finally, standardized concentrated feeds are produced on the market, which guarantee the technical specifications to customers. If the company decides to buy the feed on the market, there is a risk that the available formulations will not meet the nutritional needs of its animals. It is normal for the company to operate similar supply chains, such as poultry and pork, which increases the variety of concentrated foods that are required. In the company that produces its own food and sells the surplus to the market, it produces exchange for economic benefits but complicates the integrated management of the business. The diagram summarizes the production cycle of the balanced feed, which can be summarized as acquisition of raw materials from suppliers, for storage in silos, maintaining the independence of batches. Formulation of the balanced feed to be produced, based on orders, internal and external. The grinding of raw materials to homogenize the final products. And final processing, until you have bulk products, ready to be shipped to external customers and the farm network. To make balanced animal feed, two components are required, the macro mix and the micro mix. The first is made up of agricultural products, which are classified as cereals, associated with energy sources, and oilseeds, associated with proteins. In the micro mixture, medicines, vitamins, minerals and dyes are added to the macro mixture. After obtaining a sufficiently homogeneous and uniform product, quality tests are carried out, and it is sent to the tanks, and later pack it in polypropylene or kraft paper bags, or dispatch it in bulk tankers. If the company produces plant-based raw materials, it is necessary to synchronize the production cycles of the farms with the demand for commercial meat products, a process that involves raising animals on the farms. Therefore, integrated planning is required. The optimization of the concentrated feed production chain is based on models aimed at optimizing the planning and scheduling of concentrated feed production that meets the internal demand of the agricultural network and the external market that satisfies the demand of third parties. The availability of vegetable raw materials, their nutritional characteristics and their physicochemical characteristics are taken as a reference to determine the optimal mixtures that satisfy the formulations of the different types of concentrated feed to be produced. This mathematical problem is known as blending. The mixture of vegetable raw materials normally corresponds to a linear programming model, in which the raw materials contribute to the technical specifications, according to the percentage by weight or volume they contribute to the mixture. Technical specifications are usually defined as a range for each grade. Mixing implies that there is no predefined formula for concentrated feeding, and that it will be the mathematical algorithm that decides which is the optimal mixture to use. Within the optimization process, secondary products and polluting products can be considered. The storage of vegetable raw materials and large quantities of concentrated feed is carried out in silos, in which the differentiation of the batches of materials according to their characteristics is maintained. The attributes of raw materials are contribution to every technical quality specification, storage time, and raw material branding. A key part of the success of the PIPA system is the coordination of all aspects related to the rearing of multiple types of birds, which supply commercial products for different markets and require a fully controlled fattening process, considering the production of concentrated feed for birds of different ages and the supply of such feed on multiple farms. Since the implementation of PIPA, the gap in bird weight volatility has narrowed, because if birds of a certain age are provided with food for another time, resources are wasted. If birds are fed at an advanced age, they will not be able to assimilate nutrients. If, on the other hand, they consume food for a younger age, they will not gain weight as expected, because the nutrients are not provided in the right amounts. This synchronism became an economic benefit in Sagia. Optimization of the distribution of concentrated feeds. Concentrated feed supply chain optimization. Challenge: to develop a DSS to solve the problem of agricultural breeding and multi-plant food production. Solution: design and implementation of a set of mathematical models for planning and planning to solve the following problems: The provision of a balanced food supply considering the age distribution of life on farms, including transport and truck routing, and planning and scheduling of production in industrial plants, including the mixing of raw materials. The feed production plant is a batch process factory and should follow the optimization processes that are suggested in factories in general. Specifically, the modeling of the food distribution process to farms should be analyzed. The diagram shows the dispatch area of bulk carriers in a concentrated feed factory. The first decisions to be made are from which feed plant each farm will be served, and more specifically, each type of feed. This problem can be very simple, or very complicated. If all sheds have animals of the same age, then they consume the same type of concentrate, so, the solution is trivial, a single truck per week transporting the right concentrate. To the extent that this rigidity is released, the mathematical process becomes complicated. It is worth tackling, as flexibility will produce economic benefits, plus it may not be possible to maintain the one-age policy on the farm. A strategic mathematical model will choose the best policy for farm management, considering the cost of transport, concentrate production and variations in demand. The rigid solution is even more complicated when you have multi-purpose farms. Since multiple types of concentrates must necessarily be consumed on these farms. Therefore, a strategic model that works by events, defining when allocations should be organized, selecting a concentrated feed plant that serves groups of farms and determining the concentrates to be produced, may be the best solution. When the assignments have been defined, concentrated plant to the farm and concentrated feed to be transported, the operational problem is simplified and reduced to the route and loading of trucks. It should be noted that bulk carriers can have multiple compartments, allowing a truck to transport various types of food without becoming contaminated. It is a mathematical problem, manageable in real cases. Poultry marketing optimization. Available for Promise, ATP, is a feature intended to establish the link between products resulting from production, with customer orders or with sales forecasting. In the supply chain of animal products, this activity is related to decisions about the handling of animals, once they have been slaughtered. The challenge is to plan the use of the animals to meet the company's commercial commitments, and the solution, the design and implementation of a mathematical optimization model, which plans the use of whole animals and their parts, considering commercial commitments, expected production on farms, production cost, sales price, inventories and technical specifications of commercial products, such as breed, type, weight and volume. Mathematically, the problem of planning the allocation of live animals to commercial commitments is to find the number of whole animals, and animals per piece, that are required to meet demand and reduce costs. The questions to be answered are: when should the whole animal be used, bought, or sold? When to cut it into pieces? When to use, buy, or sell the parts? To which trade orders should I assign the whole animals, and to which parts? Which animals, from which farm, should go to a certain processing plant? The diagram presents the possible flow of products. From farms, live animals classified by categories must be sent to the slaughterhouse. At that point you can decide between keeping the animal whole or sending it to the cutting plant. If kept whole, it can go to the refrigerated inventory of whole animals. From there it can be packaged and then catered to a customer's order, or it can go to the cutting plant, at the right time. From the cutting plant, it will go to the refrigerated inventory of parts and, finally, to the packaging of the parts, so that they are assigned to the orders and thus arrive at the consumption centers. Throughout this process, the category of the live animal must be considered, which is presumably part of the technical specifications of commercial products. The cut is typical of many types of animals, such as poultry, pigs, fish, and cattle. Examples of bird parts are chicken bent, leg steak, breast, wings, whole leg, breast fillet, chicken ham, sternum, and skin. To make decisions, the benefits of marketing the animals, whole or by parts, must be maximized. To do this, the following costs must be considered. Cost of collecting animals from farms, reduce the cost of parts, cost of packaging, inventory cost, financial plus refrigeration, penalty for loss of products due to perishables, and penalty for shortfall when fulfilling existing orders can be a subjective cost. Revenue is the volume of product sales, multiplied by their selling price. Demand projection. The estimation of future demand for final products is a complex problem. To this end, Hy has developed the DEM model. The DEM model allows the inclusion of elements of different types, to represent processes of demand for goods, and/or services, with very different behaviors. The generic equation to explain the average demand is made up of the following components: elasticity of demand, price, cannibalization, pantry loading, unmet demand, temporal trend, periodic seasonalities, seasonality events, commercial initiatives, effects of global exogenous variables, effects of regional exogenous variables, autoregressive effects, moving average effects, product attribute effects, POS attribute effects, and zone attribute effects. Attention to seasons with super peaks in demand. The problem of assigning live animals to commercial engagements during exceptional periods of high demand, usually associated with special holidays such as Thanksgiving, Christmas, and Easter, involves coordinating multiple decisions to minimize costs and thus maximize the profitability of sales during the super high season. The planning of this process involves integrated planning that must cover several fronts. Farm planning, inventory management policies, reconfiguration of the distribution network, planning of refrigerated storage sites, product transport planning, and reverse logistics planning. The graph presents an example of the demand of a poultry supplier, whose demand is concentrated in the Christmas and New Year's Eve holidays. The rest of the months of the year, it can be said that the demand almost disappears. Optimization of collection and distribution in the poultry industry. Models aimed at optimizing the collection of agricultural products, and their allocation to trade commitments, which can be orders and/or bilateral contracts. Considering, among many aspects, capacity and availability contracts signed with carriers, such as shipping companies, own vehicle fleet, and enlistment capabilities. Value proposition. To economically evaluate the benefit of the value proposition associated with the mathematical optimization models applied to the poultry sector, information from the SYGEA case related to the integrated poultry production planning. The case has been published in the journal Interfaces in 1996, with the title Integrated Planning for Poultry Production at SYGEA. In 1944, in Concordia, in the western region of the state of Santa Catarina, Brazil, Atilio Fontana created SYGEA Concordia S.A., starting with a wheat mill, where he also raised pigs, which he sold in exchange for local crops. SYGEA became a global processor of pork, beef, chicken and turkey foods, as well as pasta, margarine and desserts. A national leader in all the activities in which it operated, it was one of the largest food companies in Latin America and one of the largest exporters in Brazil. In 1994, it processed 300 million chickens and 11 million turkeys a year. SYGEA's poultry production was around 21% of Tyson Foods, the largest North American producer at the time. In 2008, SYGEA had about 20 industrial plants that together produced more than 2.3 million tons of food, serving more than 70,000 direct points of sale in Brazil and exporting to more than 100 countries. In 2009, the company announced a merger with its main competitor Perdigão, forming BRF, Brazil Foods. The diagram presents the connectivity of the systems models. PIPA stands for Integrated Poultry Production Planning, developed by SYGEA. PIPA encompasses the three hierarchical levels of planning, strategy, tactics, and operation. PIPA is backed by predictive analytics, for statistical process support, and prescriptive analytics, for industrial process optimization. All the models required by the poultry company integrate an artificial hypothalamus. In the past, the vision of models was to build and run them independently, manually coordinated, executed periodically. Today, Industry 4.0 offers a new vision of mathematics for optimization. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world." Thank you for your attention.